You ever look at a complex math function and just think, how on earth can we know what its graph looks like without plotting, a million different points? It really does seem like a mystery. But today we are going to crack that code.
Okay, so take a look at a curve like this one. It's not just some random line, right? It's telling a story. It rises up to a peak, it falls down into a valley, it even changes the way it bends. Our whole mission here is to figure out how to predict this entire story just by looking at its formula.
So, that's the big question, isn't it? How do we basically become graph detectives and uncover all the secrets of its shape? I mean, we can't just guess. We need clues. We need a real method.
And here it is. The answer? The clues are hiding in plain sight, right inside the function's derivatives. The first and second derivatives, well, they're our detective's toolkit. They're our magnifying glass and our fingerprint kit for figuring out these graphs.
So first up, let's grab our first tool, the first derivative. I want you to think of it like a compass. If you are walking along this curve, the first derivative tells you at any given moment whether you're heading uphill, downhill, or if you're on a flat bit for just a second.
And here's the formal rule for it, the increasing/decreasing test. And it's actually incredibly straightforward. If that first derivative, f prime of x, is positive, our function is climbing. If it's negative, our function is falling. It's really that simple. Let's see this in action. Look at the green sections. That's where our compass, the first derivative, is positive, and the function is going up. And then in the red sections, that's where the derivative is negative, sending the graph right back downhill. So the really crucial part is this. Where do these changes from uphill to downhill actually happen? Well, they happen at special places we call critical numbers. These are the only spots where a change in direction can even happen, like the flat top of a hill or the very bottom of a valley. These are our key points of interest.
All right, so we've got direction covered, but what about the shape of that climb or that fall? For that, we need our second clue, the second derivative. If the first derivative is our compass, then think of the second derivative as our steering wheel. It's what controls the bend or the curvature of our path.
The technical term for this bend is concavity, and honestly, there's a really easy way to remember it. If the curve is shaped like a cup, we call it concave up, it can hold water. If it's shaped like a dome, it's concave down, it's going to spill water.
Now here's the more, let's say, technical definition in action. A concave up curve will always sit above its tangent lines, almost like it's being held up by them. On the flip side, a concave down curve hangs below its tangents. It's all about that relationship between the curve itself and its slope at any point.
And you probably guessed it, just like with direction, we've got a super simple test for this, the concavity test. If the second derivative, f double prime of x, is positive, our graph is concave up, it's cup-shaped. If it's negative, our graph is concave down, it's dome-shaped.
And that moment where the story changes, where the curve switches from being cupped to domed or the other way around, that is a very special spot called an inflection point. It's where the whole character of the curve's bend just shifts.
Okay, we've got our clues, direction from the first derivative and curvature from the second. Now let's put them together to find the most interesting features on any graph, its peaks and its valleys, which, mathematicians like to call local maxima and minima.
This right here is the first derivative test. It's a really powerful way to figure out what's going on at those critical numbers we found earlier. Think about it. If our direction changes from increasing, that's a positive f prime, to decreasing, a negative f prime, well, we must have just gone over a peak. That's a local maximum. And the reverse, going from decreasing to increasing, that's a valley, a local minimum.
It really is as simple as this visual. You go uphill, then you go downhill. Boom, you found a maximum. You go downhill, then you go uphill, and you found a minimum. That change in the sign of the first derivative is the absolute telltale clue that you've hit a summit or a trough.
But wait, there's more. We have another tool for this job, the second derivative test. Now, instead of looking at the direction around a critical point, this test checks the concavity right at the point itself. Just think about it for a second. If a point is flat, but the curve there is concave down like a dome, it has to be a maximum. And if it's flat but concave up like a cup, it must be a minimum. Pretty clever, huh?
So, we have all of our tools. Let's put them to the test. We are going to crack a case file directly from the source material. We're going to sketch the graph of this function, y equals x to the fourth minus 4x cubed, and we're going to do it using only our derivative clues.
Here's our 4-step plan of attack. First, we'll find our clues, calculate both derivatives. Second, we'll identify our suspects, which are the critical numbers. Third, we're going to interrogate those suspects using our tests to find any peaks or valleys. And finally, we'll map out the concavity of the entire graph to find any of those inflection points.
Okay, let's follow the plan. The first derivative turns out to be 4x cubed minus 12x squared. When we set that to 0, it tells us our critical numbers, our suspects, are at x equals 0 and x equals 3. Now for the second clue, the second derivative, which is 12x squared minus 24x. This is what we use for our concavity test. And as you can see from the chart, the second derivative is positive when x is less than 0 or bigger than 2, so the graph is cupped upwards in those areas. And it's negative between 0 and 2, which makes the graph a downward dome right in that interval.
And here is the payoff. Our analysis of the first derivative pointed to a local minimum at x equals 3. Our concavity chart showed us the bend changes at x equals 0 and x equals 2, giving us 2 inflection points. And if you look at the final graph, our detective work was perfect. The code is cracked, and the true shape is totally revealed.
So let's just recap the powerful toolkit you've basically just unlocked. The first derivative, that reveals direction. The second derivative reveals the curvature. The derivative tests let you pinpoint the peaks and valleys, and inflection points, they mark exactly where the curve's fundamental shape changes. And look, this isn't just some neat classroom trick. As the source material itself says, so much of what makes calculus useful in the real world depends on this exact skill, this ability to understand a function's behavior just by investigating its derivatives.
Which really leaves us with a final thought. I mean, these peaks and valleys, they're not just points on a graph. In the real world, they can represent maximum profit, or minimum cost, or peak efficiency. So the question is, how can we use this detective work to optimize all the complex systems that shape our world?